On the morning of October 24th, Tropical Storm Otis was heading for the Pacific coast of Mexico. Later that day, it was a major Cat 5 hurricane that would eventually slam El Capulo with 165 mph winds. The prior month, a similar pattern was observed, as satellites began dispersing images of Hurricane Lee, a major hurricane currently traveling up the Atlantic. Meteorologists observed the third fastest case of rapid intensification, when a hurricane's wind speed increases by 35 mph or more within 24 hours, ever recorded. On September 7th, wind speeds inside Lee more than doubled, boosting it from an 80 mph Cat 1 storm to a terrifying 165 mph Cat 5 storm. These types of explosive jumps in growth are becoming more common in some areas, and the consensus among scientists is that a warming planet will ultimately produce more Hurricane Lees and Otises, monster storms with the potential to double in strength before they strike communities lining the coast. Rapid intensification only crops up in a handful of tropical cyclones each year. However, a study published last month in Nature found that within 240 miles of coastlines, rapidly intensifying storms are now significantly more common than they were 40 years ago. Examples include Hurricane Ian in 2022 and Hurricane Michael in 2018. The latter leapt from a Category 2 storm to Category 5 the day before making landfall in the Florida Panhandle. It claimed dozens of lives and caused $25 billion in damage. And while some hurricanes intensify over open water, those that grow rapidly before striking landfall pose a major risk to people living on the coast. In such a situation, evacuations ordered under the expectation of, say, a Category 2 or 3 storm could prove wholly inadequate, leaving thousands of people vulnerable, a meteorologist's worst nightmare. Until very recently, it's been difficult to forecast rapid intensification, which can emerge suddenly, partly because so many shifting conditions need to align in order to trigger it. Tracking them all in real time is hard. Plus, much depends on activity in the very core of the hurricane, from where it is notoriously difficult to gather data. Scientists are now developing new methods to help them warn people of this rising threat. Recipe for a hurricane. The development of any hurricane relies on the right environmental conditions. If water in the ocean beneath the hurricane is warm enough, it releases large amounts of energy as it evaporates, which in turn creates a dip in air pressure that whips up powerful winds. The strengthening system also benefits from surrounding humid air, which locks moisture and energy inside the hurricane itself. Low vertical wind shear, where winds at higher altitudes remain relatively low in speed, also help the hurricane maintain its power. But what is it about all these conditions that makes the difference between a gradually strengthening storm and one that intensifies rapidly? Everything just has to align, says Brian Tang, an atmospheric scientist from the University at Albany. All those conditions developing simultaneously help to trigger rapid intensification. Just before Hurricane Lee's sudden explosion in power, Tang had a hunch things were about to escalate, thanks to images of the swirling mass of ice crystals and rainwater inside the hurricane. It was very symmetric, recalls Tang. That signature was like, oh yeah, this is about to really jump up in intensity. It wasn't just Tang who had an inkling that Lee was about to become significantly more powerful. He notes that models such as the Hurricane Analysis and Forecast System, HAFS, at the National Oceanic and Atmospheric Administration, NOAA, actually predicted rapid intensification for this hurricane around 24 hours in advance. Yet there were still surprises, says Jason Dunyan, a meteorologist and director of NOAA's Hurricane Field Program. I think it was pretty clear to me and other forecasters that we would see rapid intensification, that 35 mph in one day, he recalls. But it was much faster than that. By gathering more data from the inner core of a hurricane ahead of time, including via the Hurricane Hunter reconnaissance flights that Dunyan and his colleagues make, these models could perhaps be even more accurate at predicting the degree of rapid intensification that will occur. More detailed measurements are helping forecasters too. Take 2018's Hurricane Michael. A 2020 study found that satellite data and readings from buoys in the Gulf of Mexico, for example, showed a marine heat wave was underway during its approach. Similar data could warn meteorologists in the future that an incoming hurricane is about to intensify. Additionally, researchers are increasingly flying drones into the little-studied lower and most dangerous part of a hurricane, called the boundary layer, in order to gather useful information about how storms intensify. Getting into hot water, Ruby Leung, an atmospheric scientist at the U.S. Department of Energy's Pacific Northwest National Laboratory, points out that the influence of the ocean on tropical cyclones can be complex. If, for example, a lot of fresh water flows from a river into the ocean, you can get an upper, fresher layer of warm water above the denser, saltier water below. That makes it much harder for a storm to mix the ocean and bring cooler, deep water to the surface. If those upper waters remain warm, a hurricane can continue to strengthen. This effect supercharged Hurricane Irma in 2017. It rapidly intensified exactly at the time when it passed over this area with very fresh water at the surface of the ocean, says Leung. She and colleagues published a study in 2020, in which they showed how fresh water from the Amazon-Orinoco River system appears to increase the chances of rapid intensification in the eastern Caribbean and western tropical Atlantic. A similar ocean layering occurs when hurricanes produce especially high amounts of rainfall, which also adds a surface layer of fresh water to the ocean, making it harder to mix. There are already signs that climate change-induced freshening from increased rainfall in the North Pacific, for example, is intensifying typhoons, the equivalent of hurricanes in that region. Hurricanes and storms in general tend to be producing more rainfall as air temperatures rise, adds Leung, increasing the odds of intensification and creating a kind of feedback loop. Henry Potter, an oceanographer at Texas A&M University, has studied how Hurricane Harvey rapidly intensified back in 2017 as it reached the Texas Bight, a region of coastal waters in the Gulf of Mexico. One measure of the heat energy available to the storm suggested the risk of rapid intensification was relatively low, but it didn't account for the fact that the water was warm all the way down. It doesn't matter how much mixing you do, you're not going to be mixing up any cold water, explains Potter. Understanding these environmental nuances is crucial for better predicting rapid intensification ahead of time, as it becomes an increasingly common risk. Research indicates that populated areas are going to be more exposed to hurricanes in the near future. For example, First Street Foundation estimates that a significant proportion, around 40% of the population in southeastern Michigan, is potentially unaware of a heightened flood risk in their area due to increased rainfall, including from hurricanes. The overall range of tropical cyclones is also expected to widen significantly, meaning millions more people could face the devastating effects of these mammoth storms, and rapid intensification specifically in the years to come. It is a major concern, says Potter. The inevitability here is that the oceans are just going to become like bathwater in the summer, deep baths that are great for storms to intensify. Study significance. The knowledge of two unique modes associated with hurricane intensification will enhance our understanding and prediction of these hazardous events. Trying to find the holy grail behind rapid intensification is the wrong approach because there isn't just one holy grail, said NCR scientist Falco Jutt, lead author of the new study. There are at least two different modes or flavors of rapid intensification, and each one has a different set of conditions that must be met in order for the storm to strengthen so quickly. Modes of rapid intensification. The first type is when a hurricane intensifies symmetrically due to optimal environmental conditions, such as warm surface waters and low wind shear. Historical examples of this type include Hurricanes Andrew, Katrina, and Maria. The most recent example is Hurricane Otis, which unexpectedly grew by 110 miles per hour within a day, evolving into a Category 5 hurricane before hitting Mexico's west coast. The second type, which previously went unnoticed due to the peak winds not being as destructive, is linked to significant bursts of thunderstorms distant from the hurricane's center. These bursts rearrange the cyclone's circulation, enabling it to rapidly amplify, often reaching Category 1 or 2 intensity in mere hours. Astonishingly, this form of intensification can occur even under unfavorable conditions, such as opposing upper-level winds. Those storms are not as memorable and they're not as significant. But forecasters need to be aware that even a storm that's strongly sheared and asymmetric can undergo a mode of rapid intensification, said Jutt. Unexpected discovery. Jutt's discovery emerged unexpectedly during an unrelated project, where he conducted a comprehensive 40-day simulation of the global atmosphere. Upon analyzing the data, Jutt discerned that the rapid intensification occurred in two distinctive manners. Such findings were previously elusive due to models focusing on isolated regions rather than a global perspective. Real-world tropical cyclone observations further corroborated both modes of rapid intensification. Serendipitous finding. It was kind of a serendipitous finding, Jutt said. Just by looking at the storms in the simulation and making plots, I realized that storms that rapidly intensify fall into two different camps. One is the canonical mode, in which there's a tropical storm when you go to bed, and when you wake up it's a Category 4. But then there's another mode that goes from a tropical storm to a Category 1 or 2, and it fits the definition of rapid intensification. Since nobody has those storms on their radar, That mode of rapid intensification went undetected until I went through the simulation. Study implications. Concluding their research, the team theorized that many cases of rapid intensification could fall between these two modes. A storm might start with the sprint mode, but gradually transition to the marathon mode. According to Judd, a question for future research is why bursts of thunderstorms can cause about 10% of storms in an unconducive environment to rapidly intensify, even though the other 90% do not. There could be a mechanism we haven't discovered yet that would enable us to identify the 10 from the 90, said Judd. My working hypothesis is that it's random, but it's important for forecasters to be aware that rapid intensification is a typical process, even in an unfavorable environment. The research, funded by the U.S. Navy Office of Naval Research and the U.S. National Science Foundation, appeared in the Monthly Weather Review, a journal of the American Meteorological Society. Thanks for watching. To stay updated on the latest discoveries, make sure to subscribe to my channel and turn on notifications.